Very good. So my great pleasure to welcome Miguel Ohnesorge. I hope I'm pronouncing that more or less correct. It's a name that I have seen, but that's the first time I've actually met him, right? He's currently a postdoc at the University of Cambridge, but he's about to start as an assistant professor at Boston University, my alma mater. So it's good to see that the philosophy of science will continue to be alive and well at Boston University. He's written on a number of things, in particular about geodesics, both historical perspective and from a modern perspective, and I think we're going to get the historical perspective in this talk. So let's welcome Miguel.
Okay, well, thank you, Wayne. Thanks so much for having me. It's been a great joy already. I look forward to the other talks. When I first got the invitation by Chris, and I thought, oh, they must have made a mistake, all those illustrious people and then me. So, there you have it. Now you have to listen to me for 45 minutes. I'm going to talk about what I call Newton's open problem. It's one, I think, central open problems in the argument for universal gravitation and the research program predicated on it to test the theory of gravitation. Essentially, it's what I call the principle of additivity, the idea that if you have a composite body, the attraction of that body is really the result of the sum of all the attraction of the parts of that body. Okay, and that's what really makes theory universal, proportional to mass, not sort of some macroscopic feature of celestial space, celestial bodies, or the ether, or something like that. So basically, what I will do is I tell you the story of the fate of this principle, the principle of additivity in the Principia and after. And I want to look at the implications this has for how we think about evidential reasoning in this research program and more generally. I see this as sort of also, in honor of the conference, as really building on and extending work that George Smith, a dear mentor for me, has done. And he, in a sort of prescient and almost apologetic note in the paper that Lydia already so nicely discussed in Closing the Loop, after he gives his sort of authoritative account of how we how we managed to test Newtonian gravitation over several centuries, he says, I've used the phrase the accuracy of Newtonian theory in an effort to capture the results of doing this, the testing, in a summary fashion, even though what the evidence really showed about was about the accuracy of the individual principles of the theory. And so the evidence varied from principle to principle. This is true, especially if you think about the model of confirmation George proposes, because it's the individual principles deduced from the law that underwrite specific counterfactual claims about the differences that configurational details of masses and densities in the solar system make. Okay, and I'll look at one of those principles, which I call the principle of additivity. It's not Newton's term, it's mine. If you have a better idea, let me know. But essentially what I mean by that it can be explained most clearly if we think about the argument in Book 3 of the Principia, sort of scaffolded in different ways, in different steps. In a first step, what happens in Proposition 124, essentially what Newton is committing to is, how Stein nicely put it, right, inverse-square acceleration fields external to celestial bodies. That gives you a lot. It gives you, among other things, the moon test that Bill has written about nicely. From Proposition 5 to 6, we're getting another commitment, the commitment that the third law of motion applies to gravitation, and gravitation is a force of interaction. So now we're committing to mutual inverse-square attraction between celestial bodies that is proportional to the masses of each. As Howard Stein has shown, and George has done historical work elaborating, Newton saw that this was actually a problem in his argument that he need to give separate evidence that the law of motion that he had some confirmation for the case of collisions really applied for motive forces due to gravitation. But then from Proposition 7 onwards, and already slightly implied before but spelled out most clearly, we're committing to something else, right? We're committing to the principle, or Newton is committing, that if you have the attraction of a celestial body, what it really is composed of is the sum of the attraction of the parts of that celestial body, and that gives you universal gravitation. It gives you a theory of in which gravitational force is proportional to mass and distance generally, and not just at the level of celestial bodies. Despite being presented as a corollary to the law by Newton, this scale invariant additivity is in fact an important premise of his inference from taking terrestrial and celestial acceleration fields, starting with that and then going to a force mathematically characterized independently universally proportional to mass and distance. Okay. And just to, like for those not deep in the Newtoniana, just to give you a sense of how important Newton himself considered this principle to be to his overall program of mathematical philosophy that the Principia is supposed to initiate, is the preface to the first edition, where he says, well, I wish we could derive the rest of the phenomena of nature by the same kind of reasoning from mechanical principles, for I am induced by many reasons to suspect that they may all depend on certain forces by which the particles of bodies, by some causes hitherto unknown, are either mutually impelled towards each other or cohere in regular figures, or are repelled and recede from each other. So the idea is really this additive, you get the macroscopic forces additively from microscopic forces. Okay, I mean, there's an interesting close connection to Newton's matter theory that we can discuss in the Q&A. But in general, this principle is really important for the broader vision, not only for gravity, but that Newton sees for mathematical philosophy in general. In brief, what I'm going to tell you historically today is summarized in these slides. I don't like to keep people waiting. This is what I'm going to tell you. I first want to show you that this was perhaps the weakest but a crucial link in Newton's argument for universal gravitation, which I already tried to motivate. I'll then run you very, very briefly through a lot of history and show you that in the early 19th century, the possible force laws for gravitation at the micro and meso scale, right, so ordinary and microscopic, really still remained extremely loosely constrained by the evidence that existed, which is all macroscopic. All the evidence, the key evidence came from measurements of the Earth figure, assumed to be a figure of equilibrium, and variation of gravity on its surface with latitude. Now, what this means at small scales, like whether you really get inverse square gravity down to very small scales, is only very loosely constrained. And mostly this idea that you can get a microscopic force that's then additively composing the macroscopic force is really still a matter of inductive faith, right, in the manner of Newton's third rule, or perhaps also of metaphysical parsimony, the attractiveness of this particle force ontology. Now, something changes after 1800. For once, with the sort of demise of the Laplacian program in physics, this whole ontology of microphysical particles and inverse square forces, I think for many is no longer really attractive. So that undermines some of this inductive faith. And electrodynamics, I mean, is an important example of a force that looks quite different in important respects. And many consider foundational. And there are important sort of empirical discrepancies in mesoscopic measurements. So that leads to worries and attempts to figure out where and if Newton's law breaks down at short distances if we directly measure it there. To the surprise of many, Newton's theory proved extremely successful, even at the meso and micro scale, up to the early 20th century, when we have more mesoscopic study of gravity anomalies characteristic of Earth's gravity field that are sort of smaller, and direct measurements of short-range attractions in the lab. Okay, this is the story I'm going to tell. Why does it matter? For one, I think I want to motivate at least the idea that at least at these scales, for the 19th century, we should rethink Newtonian gravitational mechanics really as an open-ended research program, by which I mean open-ended not just perturbationally speaking, open to new models for perturbational disturbances to apply the theory, but also in many respects open to revision of its basic principles, such as additivity at small distances. This is contra many famous stories about their history by Ewell, who was a participant, by Kuhn, obviously, standard textbook history, and even very, very slightly contra George, and I can tell you where exactly I think, from personal conversations, I think we might depart. And it's, I think, just because I looked at some of this material and George couldn't do all the work for everyone. So granting that, which I'll try to motivate, I then want to look at what exact difference that change in evidential reasoning made for the evidential support in Newtonian gravitation. So what do we have at the end of the 19th century due to these cross-scalar tests that we didn't have at the beginning of the 19th century? And I'll suggest I'll try to flesh this out. This very much, I'm thinking on my feet here, by this a label of what I call evidential closure. And I'll try to make exactly what I mean by that later. What I consider this sort of an even stronger form of evidence for the Newtonian theoretical models than just the robust theory-mediated measurements. And it also, importantly, puts tighter constraints on future theories. Good. I've talked a bit about universal gravitation. I'll move on by talking a bit about the macroscopic evidence up to the 19th century, coming from this nice field that I like a lot, the physical geodesy. Then talking about cross-scalar testing in the 19th century, early 20th century, and then draw some philosophical lessons from that. Okay, let's start with Newton. Now, Newton was, we know from manuscript evidence, quite aware that he wanted direct empirical evidence for additivity. He thought about this at least from 1686, when he learns from Halley that the measurements by Jean Richet, who took a pendulum clock from Paris to Cayenne at the equator, calibrated to astronomical time in Paris, that the pendulum lost time at Cayenne, indicating a decrease in surface gravity. So he started to think about relating this to the overall argument, started to writing theoretically on it. The main problem Newton faced for, in general, getting evidence for additivity is that he had shown so beautifully and remarkably that if you have spherical bodies, then the attractions of these bodies outside seem to not really depend on whatever happens inside, right? At any point outside of a sphere, you get the same attraction as if you just have a more massive particle at the center of the sphere. The problem is that if you, as many others with other ontological commitments, like Huygens, for example, if you accept that gravity is an inverse square force, or a force with some other power law of distance, so it just varies as a function of the center to the body, you can, for spherical bodies, buy everything that Newton tells you without committing to the idea that, in fact, it shows anything about without the internal parts, the internal distribution of mass, making any difference to any actual measurements. Okay. Well, but Newton realizes this is not longer true if you look at oblate spheroids, okay, ellipsoids. For ellipsoids, if you believe in a simple 1 over r or 1 over r squared gravity, such as Huygens, it is true, even for ellipsoids, if you're at the pole of an ellipsoid, non-rotating, just a geometrical figure, then the distribution of matter, the shape, let's assume it's homogeneous, right, of that body, really does not make a difference, okay? So it's a bit more squashed. If you're at the pole, then the attraction of that body is the same as if it were a sphere, where the diameter of the sphere is equivalent to the polar axis of the squashed ellipsoid. But if you believe in particle-to-particle gravitation, like Newton in additivity, well, then you get the attraction of the composite body by integrating or doing quadratures, as Newton would have it. In fact, Niccolo Guicciardini nicely showed us in this proposition 91 corollary 2. Newton, in fact, solved this problem using quadratures. It's one of the problems in the Principia that he doesn't manage to solve geometrically. He solves it in quadratures and then translates it back in this geometric construction that everyone found very hard to understand. But the key point is, okay, the shape of the figure matters here, right? So if you're at the pole and the figure is squashed, then you get a different value for gravity. It also means if you move from the equator to the pole of such a figure, you get a variation in gravity. So the distribution of matter makes a difference, as it does not in the sphere. So you have to get some evidence by looking at the attraction of oblate spheroids, or a consequence of that attraction. Thank God we're living on an oblate spheroid. Okay. So I just need to. So Newton starts to work on the figure and attraction of the Earth. Once he learns about Richet's measurement, he assumes that the Earth is in a state of equilibrium. That's how the shape of the Earth relates to the law of attraction. He has sort of a stipulative definition of that. He doesn't have partial differential equations. So he defines the hydrostatic equilibrium of a rotating spheroid by this nice principle of canals. Comes up first thinking about tides, but it doesn't really work. He takes it here. The idea is just that if you have a rotating body and you have two canals of water connecting the pole and the equator to the center, okay, then you can define that body to be in hydrostatic equilibrium. So as a way to make tractable the idea that it were entirely fluid. If the weight of these canals under rotation is exactly the same, since you have the rotational inertia, this means that the equatorial canal has to be extended relative to the polar canal. The quantity then ellipticity of the equilibrium figure becomes your test. You can measure that quantity, and the value you should take under rotation in equilibrium depends on the law of attraction between the parts of the body. Okay, that's the idea. Newton gives you two predictions. One is directly the ellipticity of that equilibrium figure under rotation. I won't talk about the derivation. I've written on it. I'm interested in it. Ask me about it if you want to know more. Newton comes up with a prediction. He revises it over the different editions of the Principia of the Earth equilibrium figure being an ellipsoid with an ellipticity of 1 over 230. And as a corollary, you have a variation of surface curvature with latitude that is roughly as the squared sine of the latitude. It just tells you it's an ellipse. And then again, what is the variation of surface gravity? We know just that surface gravity varies on oblate spheroids. With latitude on such a figure, again, it's a sin square plus a constant depending on ellipticity of latitude. So you can see here Newton's, this is in the second edition, he adds this table, Newton's predictions for those two values. It says the pendulum there because, I mean, as I indicated, you measure surface gravity by looking at the length of a pendulum clock swinging with a period of exactly 1 second. So if gravity varies, you'll have to adjust the length to preserve the period. You can measure variations in surface curvature by looking at the changes in the length of 1 degree of a meridian. This is done, I mean, up to the 20th century by doing triangulations. It's just a sophisticated form of measuring distance optically. So you set up a network of observation points and triangular shapes. From the angles, you can determine the sides of that network composing part of the meridian. Astronomically, you make sure it's on a meridian and covers the distance of 1 degree. Both of these you want to reduce to sea level. They will become important in the 19th century, right? If you're in a certain altitude, the matter might make a difference, the attraction of that matter. Okay, Newton never finds closure with the data available. He works on this. As George taught me, it's the most revised proposition throughout the 3 editions of the Principia, which tells you how much he worried about these results. This is revisions I found in the Newton papers in Cambridge from the 2nd to the 3rd edition. So he repeatedly adjusts it, recalibrates it with measurements done by the French. But he never finds closure with the measurements. And I mean, like, one key reason is that, of course, the theory is also not very well developed. We're talking about here a very nice case of a Newtonian idealization. Why do we do? Because all Newton's results depend on homogeneous density, right? All that nice principle of canals, Newton only solves it by assuming uniform density. Of course, on his theory, stratified density will make a difference. And if we're dealing with a Newtonian idealization, as Lydia so nicely explained, sorry, this should say accurate, it would only hold accurately under these specifiable circumstances, uniform density. Well, what do we need to do then in Newton's method, as George characterized it? Well, we need to figure out the discrepancies from the prediction of that model in the actual data in those 2 methods of measurements. And then we have to see if we can find robust gravitational causes that behave according to Newton's theory for all those discrepancies, variations in density, that conversely exactly make the differences that they ought to make according to the theory. A major advance here is in 1743. Alexis Clairaut, the great French mathematician, physicist, who shows that the ellipsoid is also first-order equilibrium figure for rotating fluids that are stratified, so you have increasing density towards the center. It's just that it's bound between 2 values, 1/230 for the Newtonian homogeneous case and 1/577 for one where the density is the mass is concentrated at the center. And he gets this nice result, which is still called the Clairaut's theorem, which gives you the variation of surface gravity and with slight modification surface curvature on the surface of that equilibrium figure, where E then depends on the density. M just tells you how strong the centrifugal effect is at the equator as a fraction of equatorial gravity. Then by 1799, what Laplace managed to show is that there's in fact some good evidence once you have this density correction that contemporary pendulum and arc measurements converge around values within that interval between 1/312 and 1/333. And that range, which implies an increasing density, though we don't know the exact power law that's underdetermined, Laplace also vindicates by looking at other phenomena, the robustness of it, that depend on the density. That's the precession of the Earth, so the change in its rotational axis, due to the attraction of the sun and moon on the equatorial bulge, and the specific pair of lunar perturbations that also depend on that equatorial bulge. Okay. If you want to look at Laplace's data, I plugged it here in Excel the other day. Thought it might make it more visible. Give you a sense of like what evidence there's available at the time, which isn't too much. Okay, you have here the length of the seconds pendulum relative to Paris. With latitude, the red gives you the best statistical fit. Laplace actually takes the medium for the ellipsoid, and the green are the actual observations. I can tell you in this case, this is actually in the limit of observational error at the time. Laplace is quite careful in his discussion. So this is quite a good result. It looks not as nice if you look at the measurements of 1 degree of meridian and surface curvature. And I'll tell you about these anomalies that they'll become more important. There's also just seven of them around, where you have discrepancies that are beyond observational error. So if you take the large ones, you would get discrepancies of around 200 meters in the measurements of 1 degree, which are roughly 25,000 meters. So 25 kilometers. So you think it's small, but given the precision of these optical measurements, that's quite significant. It can't be an observational block. Okay, so that's by 1800. Laplace celebrates this as a crowning achievement of the celestial mechanics. This is in fact the problem in my sort of calculations that Laplace spends the most time working on of any problems in the celestial mechanics in the range of pages, because it bears on the universality of the law, right? And Laplace wants to show that gravitation is a particle-to-particle force. His whole program is supposed to generalize from the Newtonian case to other forces to show that they're also particle-to-particle forces. So you think it matters that it works for gravitation. And he concludes that universal gravitation, given this data, is the true cause of all these phenomena. Inequalities of the attractive forces of the planets that he has thus corroborated depending on the distribution of mass. So irregularities in the surface and internal parts of the body, they disappear at great distances so that we then get the simple inverse square law in astronomy. So here you have additivity. He is even more explicit in this more popular discussion in the system of the world. He says all the particles of matter mutually attract each other according to the law. Okay. Now, note, of course, that the generality of this conclusion, not qualified, is not entailed by that evidence that I showed you, right? We look at aggregated attractions of large-scale features of the Earth over very large distances. I mean, if you take the modern terminology, post-Laplacian, in fact, we're looking at the second term in the spherical harmonic solution to the Earth potential function. That's very, we now have like thousands of terms, right? If you use your GPS, you're relying on them. So it's quite weak in how it bears on the mesoscopic and microscopic applicability of gravitation. So there's a huge leap of inductive faith that Laplace is taking. Okay, that's the 18th century, 19th century, and there's much more in the 18th century. I could talk about this for hours, but I don't want to bore you, so ask me if you want to know more about it. 19th century, two things change, as I indicated, that matter to what I'm interested in here. The first change is, I think, a metaphysical change in outlook for many people in this research program. You have advances in electrodynamics in the 20s. The work by Ampere is very important. You have the failures of Laplacian theories indicated based on a particle-to-particle inverse square force ontology in other fields of physics. Caloric fails, capillary action, the Laplacians can't really solve. The Laplacians are also not the ones making the crucial advances in electrodynamics, with some exceptions. So there's a general laws and attractiveness of every force being a particle-to-particle force, just like gravity. And there's, in fact, a direct historical trajectory to what will later be called the electromagnetic worldview that takes electromagnetism as the basic model of fundamental forces. There are empirical problems, and that links back to the discrepancies I showed you in Laplace's data that he doesn't manage to account for. There are gravity anomalies. So more data becomes available from geodetic surveys. And in fact, there's many more irregular variations in surface gravity and curvature of latitude than anticipated. There's also a serious failure of covariance between these two parameters, so they entail different values for the ellipticity. So there's also empirical problems already at the mesoscopic scale. This is very nicely, the outlook is very nicely expressed by Herschel, who sort of combines these two influences, who writes in his Physical Astronomy in 1829. This was sort of the standard text introducing Laplacian methods in the UK. Teru Miyake has a wonderful article in the George Smith Festschrift on that, on the physical astronomy. Herschel writes that with regard to small distances, we have no distinct proof that within a few inches or even miles from a material point, the law of gravity may not begin to deviate appreciably from the Newtonian law. And he goes on, at much closer intervals, we are certain of the existence of attractive and repulsive forces following a widely different law, and by what imperceptible gradations these shade into that of gravity, or whether they are to be regarded as distinct from it in their nature and origin, is a point whose consideration seems reserved for a much higher state of science than we can boast of having yet attained. He goes on, in other sciences, when an induction of moderate extent has led us to the knowledge of a law which we conceive to be general, the further progress of our inquiries frequently obliges us either to limit its extent or to modify its expression. To those who are familiar with the history of chemistry, instances of this will present themselves at every turn. In physical optics, the general representation of all the series of polarized tints, the colors of natural bodies by a certain universal scale, Cartesian law of refraction, together with innumerable other laws, simple, natural, and resting on extensive inductions, have all been either overset, extended, or materially modified by the progress of science. Okay. Now, the empirical problems, gravity anomalies, the most important work here is by George Biddle-Airy. At this point, he has Newton's Lucasian chair in Cambridge. Later, he becomes the Stradivar Royal. He works on this extensively, starting in the 20s, all to the 1850s. His first major paper in 1826, in the Proceedings of the Royal Society, he notes that the ellipticity of the Earth by the most recent and most reliable pendulum measurements by Edward Sabine, apparently the most deserving of confidence, differ considerably from the ellipticity generally believed indicated by geodetic measures, meaning the measures of surface curvature. By the 1830s, he writes a whole massive treatise on the figure of the Earth in the same encyclopedia series, Encyclopedia Metropolitana, that Herschel's physical astronomy appeared in, which is called the figure of the Earth, but is really a really important contribution to gravitational physics, and is not really appreciated as such. And you could figure out that it is if you read the opening, where Airy says, well, what this is essentially is a collection of various classes of observations which have been made for the examination of that part of the principle of gravitation which asserts that the attraction of a mass is the sum of the attractions of every one of its particles. Airy, I'm not going to bore you with more data, but Airy vindicates serious gravity anomalies, serious scatter, so even in the surface gravity measurements he collects. Now what you can see clearly is the much broader range of data. And he concludes that we must endeavor to ascertain whether these observations are consistent with the principle of universal gravitation. And if we find them to be consistent, then we must examine what alterations we have to make in the other suppositions of our theory, such that they can be made to represent the facts of observations. So the question then becomes, can we identify local disturbing masses in Earth interior topography that explain the exact magnitude and context of any of these anomalies that we detect? Okay. Airy comes up with a actually two-pronged research program of addressing this issue. One is sort of just an extension with a more sophisticated mathematical theory of the Newtonian perturbational program to the mesoscopic scale. It's the analysis of gravity anomalies. It's taken up all over the world. The question then is, well, as I just said basically already, can we get all the deviations from the ellipsoidal variation of surface gravity and the elliptic meridians, and then the conflicts between the ellipticities entailed by the two measures? Can we find identifiable masses that explain them, that make exactly the right differences? And this is a typo, on gravitational attraction, it should say, not gravitational. The second part of that program is, though, directly experimental. It's laboratory measurements of sort of mesoscale, microscale attraction. Two of these measurements existed before, in fact, 2.5. Maskelyne on the measurement of Schiehallion, the attraction of Schiehallion in the Scottish Highlands, and of course Cavendish, torsion balance experiment. Now here's the important point. Cavendish in 1798, in his paper, he discusses the possible objection that the inverse square law does not hold at the distances that hasn't been tested, and he said it's absurd. I don't have to actually engage this. He also doesn't vary the masses, right? So he's clearly not interested in testing Newton's law. But I found I think the masses part is very well known, but I found it really striking that he actually discusses deviations at short distances and says, well, a priori, this is absurd, so I don't have to deal with it. So the research program construing this as a test, which really takes off, as I try to indicate with just some citations in the second half of the 19th century, really comes after Airy, in this quite influential paper, identifies it as an important open problem to test gravity at short distances. Okay, then the question here becomes, can we show that at those small distances, the attractions still uniquely depend on mass and distance in the way that the law dictates? Okay, I'll run you through these, both of these horn in a way of that research program quickly, so we have some time for philosophy in the end. Gravity anomalies, the crucial breakthrough here becomes the theory of isostasy. The theory of isostasy basically tells you that if you have density surpluses in the Earth's crust, or density deficits, say in the oceans, then these will generally be compensated at a specific depth by either horizontal variations in density in the Earth's crust, or by a sort of balancing of the Earth's crust and the liquid but more dense mantle of the Earth. So there's a striving through equilibrium between those two layers. And that explains gravity anomalies. Why is that the case? Because what happened before, as I told you, you reduce gravity observations to sea level. Okay. Now what you do is you correct for the matter between your observation station and the level of the sea, because it's supposed to induce a disturbing factor. Now if you do that on the continents, and you sort of you correct for that, but in fact all the topographic corrections you apply are balanced out already by density deficits below. You'll introduce a systematic error. So here you have a sort of a perturbational explanation of these problems. You can see clearly the difference is made also to the aggregate ellipticity values. Helmut is the very important German geophysicist, geodesist, first applies them systematically. You can see that his values for surface gravity sort of deviate, for ellipticity deviate significantly. In fact, they're the first ones for which the two methods finally agree. I've written on this separately, but finally agree again. Once you have these corrections in place, you get an agreement with the surface curvature and surface gravity measurements of ellipticity. This is only by the late 19th, early 20th century. And you then have the first standard model that's accepted in the 1920s of the Earth's shape. Second, the experiments on gravitation. What happens there? Well, I think most of you will probably be familiar with this, but just, I mean, the basic idea of these experiments is you look at it like an equilibrium system, like a torsion balance, or this is just a normal balance, and then you look at the deflection of the equilibrium state by a laboratory mass, okay? And then you compare the attraction of that mass to the attraction of the Earth at large. So you can, depending on where you are in time, infer the mean density of the Earth, or you can infer the gravitational constant if you vary the masses. Well, one important point, I won't run you through all of this example of Cavendish's, but one important point is that to test Newton's law, especially the distance dependence with this measurement, you need to, of course, need more than one measurement, right? So even in principle, Cavendish could have, not with this measurement alone, tested that, because essentially if you infer the mean density of the Earth, you're relying on the law, right? So what you need to do is show that at different values for r, you get concordant measurements of the Earth's mean density or the gravitational constant. Okay, so these, at least the laboratory measurements, they turn out to be quite successful. You get a nice convergence towards the end of the 19th century. But then you might want to ask, okay, now analogy to the perturbational testing we do in the celestial mechanics, we're not testing here really like sort of the whether the perturbations affecting these measurements also only dependent exactly on Newtonian masses, because we're in the lab, we set it up in such a way that we avoid perturbations. But what happens, in fact, which I was long ignorant of, between the 80s and 1880s, after the 1880s, that there were many experiments set up to test, so what is exactly the converse of that, right? So can we induce perturbations by other effects that are not gravitational? So, for example, if we change the chemical composition of the masses, I mean, this in a way goes back to Newton, but for example, we can explicitly look at crystalline structure as well. This is new. We can vary the media in analogy to electromagnetism, right? So we put some sort of constraints between the different masses, see if it changes the attraction. We can vary the temperature, see if there's a temperature dependence. And then we can test if there's some sort of polarity, some directive character that appears. And by 1908, Poynting, who's, in my view, perhaps the leading figure in this program, he concludes that while the experiments to determine G are converging on the same value, the attempts to show that under certain conditions it might not be constant have resulted so far in failure all along the line. No attack on gravitation has succeeded in showing that it is related to anything but the masses of the attracting and the attracted bodies. It appears to have no relation to physical or chemical conditions of the acting masses or to the intervening mediums. Some of the qualities we try to find, qualities that characterize electric and magnetic forces, may just have no counterparts in mass. So by the early 20th century, you have quite impressive cross-scalar evidence for the principle of additivity. And I'll run you through these. These are my favorite. These are both in the Enzyklopädie der Mathematischen Wissenschaften. It's quite an important collection, the German language. So some of them have been translated in the early 20th century on the state of physical science. In the volume on astronomy, Samuel Oppenheim, Viennese astronomer, he says, looking at all the data, he concludes that the calculation of the flattening of the Earth from pendulum measurements on the surface and its comparison with geodetic determination shows an agreement that falls within the theoretical limits derived for them. The same is true for calculations of the Earth's average density from measured gravity, deflections, and the analogous laboratory experiments and measurements. So we can conclude that the inverse square law seems to be guaranteed up to the same precision within the distances of a few meters up to the Earth radius of 6 millimiles and so on. The even nicer one I like from Zenek, which is the part of the encyclopedia directly dealing with gravitation, is where he says, well, with this, however, at the beginning of the 20th century, we return to the view of the 18th century, to the view that takes gravitation to be a fundamental property of all matter, which I like a lot because it shows you how much the expectation was in the 19th century that we find it to be different, right? Somehow related to electromagnetism, and there was in fact an open problem. So by the early 20th century, and against many expectations, the Newtonian gravitation has been shown to account for measurements and all known, real or artificial, possible systematic perturbations of these measurements from small distances up to the celestial scale. So you finally have what I would call cross-scalar evidence for its additivity. Good. What does all this mean? What implications does it have for philosophers interested in evidential reasoning? Well, first descriptively, I mean, one thing I hope to have made plausible is that by the early 20th century, or throughout the 19th century already, the evidential reasoning about additivity of Newtonian gravitation combines two types of question. The one is the one we know, that George has written about so much, and that is well known from already from Newton and Laplace, is the question whether gravitation is really sufficient to derive not only models that should be exactly true or accurately true under ideal conditions, but actually robust sources for all discrepancies from such idealizations in empirical measurements. Okay. So second question, I think that's very nicely first explicitly asked by Herschel, which is, well, what exactly are the region within the parameter space of the theory where we have tested the previous condition, this sufficiency condition? Where do we really know that only the causes described by the law make the difference and exactly the difference they ought to make? So the question then becomes philosophically, to me, that I'm asking myself a lot these days, how do successful efforts at answering the second part of these questions asked about evidence change the evidential support for Newton's law by the end of the 19th century? And my idea of fleshing this out is what I call it in sort of a form of evidential closure. It's clearly a hint to George, though I think it, as I said, it's more extensive. And I take evidential closure to mean a situation where we can identify a non-trivially extended, closed, and continuous region in a theory's parameter space across which the functional relation that the theory asserts, in this case is, of course, the law of gravity, is empirically sufficient to account for any variations in the magnitude of the quantity. In this case, it's the force. And by empirical sufficiency, I'm just trying to capture, what is the notion of empirical success in the perturbational method, right? So the requirement there is that all and only the causes or contributing causes specified by the theory, masses, densities, and so on, make a difference to x to the force's magnitude, and that this difference then is exhaustively characterized. It's exactly the inverse square proportional to mass difference that it ought to be. Okay. Why does it matter? Well, here's some possible scenarios, some that I think are not sufficient to answer the question. You could think we increase our inductive base, more enumerative confirming instances. Okay. So across different scales. Before we have, by the end of the 19th century, we just have more theory-immediate measurements quantitatively of the parameters that we're interested in, conducted, forget the last bit, the different background condition, that only matters for the robustness argument. But you could think, okay, we increase our evidence base sort of in a counting kind of way, counting instances. Lydia mentioned this, sort of a received rejected view. But you could think about that is a possible way of making sense of this. The second option is sort of what I would call simple robustness, as is very often discussed in philosophy of science. Okay, so you have a more diverse range of measurements now under different conditions. That's why this shouldn't be in the first one. And they all agree on the parameter value that the theory predicates. And I think neither of those is fully satisfactory. Because you could think about it applying in very different cases. Okay, you could say, okay, we have diverse evidence for, say, Snell's law of refraction, but clearly there's something different to this case. You could think about even purely qualitative generalizations where you have some sort of robust support. You could think, okay, I think all Canadians are friendly. Okay, people tell me this. Canadians are really friendly. I think I agree. So all Canadians are in many different circumstances, caffeinated, not caffeinated, okay, they all seem to be friendly, right? So that's a robust evidence, right? Clearly there's something different to the evidence that we have in this case. So here's, I think, an important part of the answer. And it lies in what I put in that definition before, this idea that you have this closed continuous region of the parameter space. And thinking about Simon's comment, it made me realize this is very anti-Popperian of a thing to say. So what we have is that we have an inductive generalization which is supported not only by more diverse theory-immediate measurements, but in fact theory-immediate measurements conducted in a closed and continuous region of the parameter space of the theory. I think this is roughly analogous what in a measurement theory is often talked about factor independence. It's important in the axioms of conjoint measurement, where essentially what we require of a quantity is that on the empirical side is that we want a functional relation based on the order of some indicators of that quantity to be independent of their specific levels. So, and you can think about this easy as masses and distances here. You could think at any level, you want at any level of B, you want the difference that a variation in A makes to be exactly the same, and then conversely, if you fix instead of B, you fix A, and then you have the difference in B being exactly the same. So the question is, well, can we? I think the evidential reasoning is better cashed out in the support by a test question that is, can we identify a continuous and closed region of a parameter space across which this covariance, and only that covariance that the theory describes and is sufficient, really holds. But there's a sort of a tandem to this, which is perhaps I think what matters most, and is brought out very nicely in this quote by Poynting, who I featured already in this experimental work, who was one of the people who really was convinced. He really didn't like the way that people interpreted the gravitational constants when he, among others, introduced it, especially Boyce, another person in this research program, as applying all across the universe, because he thinks, okay, we have a constant so that we can find variations and makes testing easier. And he's convinced that there will be some a revision of Newtonian theory at some point at small distances. And he sadly concludes, right, that gravitation still stands alone. The isolation which Faraday sought to break is still complete, yet the work he's been describing is not a failure, the experimental work. We at least know something in knowing that the qualities gravitation does not possess, which qualities gravitation not possess, and when the time shall come for explanation of all these laborious and at first sight useless experiments, they'll take their place in the foundation on which that explanation will be built. Okay, how could we make sense of that? I think roughly like that. Think about all the possible ways in which theory could be superseded. And I think in all of them it makes it easier to come up with a successor theory, that you have this continuous parameter space. One, you can think about a tiny Clairaut-type modification for Newton's law. He posted this in the 1740s. Okay, you have an extra term, and we formulate it in such a way that only at small distances it features, okay? Now, it's good if we at least have a non-trivial large region where this does not show up, because we can constrain that extra term, okay, the values of it. Good. Another possible scenario. That's just another cause, another physical quantity that makes a difference to gravitational force, and it just only makes that difference at small distances. Maybe it only exists there, or it's just very specific, say, circumstances. Then at least the absence of that cause within the bounds of evidential closure will guide us to identify what it is once we detect the discrepancy. Okay, we can ask, okay, what is it plausibly based on background knowledge that could happen at small distances that is absent from all those rich, domain of testing that we were operating in before, or at least, if you think it's sort of a continuous difference that it makes, we can constrain the function similar to here. That describes that difference. And then the final case is, you could think about the theory as fully superseded, I think, as happened with GR. So what we have then is that the bounds of evidential closure at least constrain general or specific limit case relationships to the new theory, and that can be, as like Norton and Janssen and all these people working on the origin of the field equation have shown us, was tremendously important to Einstein. It was always the condition that you have to recover the Newtonian Poisson equation in the weak field limit when he tried to come up with the field equation. So here's another way this can be useful. For specific limit case relationship, there's this nice paper that at some point will be published, I hope, by Chris and George. They show this, that Newton did exactly the same in section 10 of the Principia, not the same, a similar kind of reasoning in section 10 of the Principia for Galilean gravity. He shows that it at least recovers, even in the Newtonian case, the results of pendulums if the radius to the center of the Earth is just large enough, even though in the Earth it's not an inverse square variation of gravity, but linear variation, and so on. And you don't have, gravity does not act in parallel lines and all these kinds of things. Okay, I'm on time. Wonderful. To conclude, I just give to you what I said in the beginning, and then we can start discussing. I try to motivate the idea that, at least at the meso or macro scale, we should, in some sense, rethink Newtonian mechanics, gravitational mechanics, as for a long part of its history being a more open-ended research program than is generally assumed, one that was open not just to new models, but revisions of basic principles like additivity. And granting that you agree with me on that, I think we can learn something philosophically. We can learn what exact difference scale invariance in testing makes to evidential support, because that's what's new in the 19th century, in my opinion. And I think you get what I call evidential closure. You get a stronger form of evidence than just the robust theory-mediated measurements alone. And as a result, one reason this evidence is so useful is you get tighter constraints on partially or fully revised future theories. And with that, I'll leave you to it. Thank you.
Thank you. That was absolutely sorry. Okay, I got it. Yeah. The fascinating talk. I learned a great deal from it. But I do have a question which is not really at the center of what you're doing, and it's always a bit of a shame that you're asked something slightly at right angles, but and it's to do with paradoxes that arise in the cosmological context, and in particular von Zeilinger. So Zeilinger was already writing about this in the 1890s. Poynting would have known these writings. He was the most influential astronomer of his time, and he was showing that there's a genuine paradox built into the inverse square law. And this specifically relating to tidal forces. It goes as 1 over r cubed, and you integrate over an infinite uniform distribution of stars, and you've got a 1 upon r, you've got a logarithmic divergence.
Yeah.
So, people might have got really bothered about this, and this might have been at the focus of attention, but it seems not. Now, why is that?
That's a very good question. I don't know. I mean, I haven't. It's not referenced either in either of the sort of widely read pieces on the empirical side of gravitational research at the time, as well, by Zanuck and Oppenheim. Oppenheim, I mean, he's an astronomer. He would have known. It might be that I'm missing something. I mean, I'm sure they might have even known personally in the case of Poynting. I'm afraid I don't have a very good answer. I don't want to say something,
Well, I think the fact that that you don't see it in the literature that you were studying shows it did not have impact.
Yeah, that is true.
And that is curious, though. I mean, that sort of sounds very puzzling. It's not as though Zeilinger was a minor figure. I mean, so I'm very puzzled at this.
Yeah. Well, now I'm puzzled too.
Can you also just tell me, were Bentley's letters with Newton published early in this period? Bishop Bentley and Newton, were those letters published early on? Because were those read by people? Because that exposed the another sort of paradox in cosmology in Newton.
I don't know when they were first published. Maybe I can defer that to Chris or Bill.
Anybody know?
I don't know, actually.
Yeah, I'm not sure either.
That's a good question.
Yeah, I don't know.
Sure.
I mean, No, I don't.
I mean, there is a case that cosmology was a sort of blind spot.
Yes.
And people thought it just wasn't appropriate somehow.
Yeah. I think Bill.
This is just. It would be interesting to compare this with the Cavendish not varying the masses.
Yes. Okay.
I mean, because that made such a huge. I mean, it was sort of an obvious thing you'd want to do, but nobody bothered.
Yes.
And it sounds like a similar thing going on here.
Yeah. No, it's good. I mean, in general, there's very little concern, as far as I'm aware, given to the question of how tightly. That's something that I'm often confused about, historiographically. The question of how tightly exactly is the mesoscopic or microscopic force law constrained by the macroscopic evidence we have for inverse square, right? What combinations of different force laws, not violating additivity, can we imagine that would still give you inverse square given some weird density distribution? You think, I mean, I know Poincaré worked on, and he was very interested in this, in the theoretical side of the geodetic problem on the theory of equilibrium figures. His work is sort of the last one in that tradition, before it's being picked up in the 60s, really, again, by Chandrasekhar, this theoretical problem, and then it becomes really important in astrophysics. And he's quite interested in that problem. But again, I think he's then writing at a time where, given the laboratory measurements, the problem is seen as less important, so he doesn't worry about it very explicitly anymore. But yeah, many open questions.
So I was struck by the, and apologies if I don't get this exactly right because there is so much information to try to process
Yeah, I'm
and
sorry
synthesize
about
in the talk. The history of attempting to and eventually succeeding in resolving the tension between two different ways of measuring surface gravity, right, like pendulum and the geodetic methods.
Yes.
That you sort of mentioned at the end, there's this German guy at the very, like, in the early 20th century who seems to actually resolve the tension and get agreement between different ways of measuring. That sort of long history of attention that then gets resolved, I mean, that's one of the things that I find so striking and interesting in closing the loop. But that didn't come out in the final section where you focus on evidential closure. I'm wondering if you see a relationship between the tension resolution and evidential closure, or if these are just separate things.
Yeah, no, that's very good. I know it was very dense. Absolutely. I think there's a relationship, right? Because if you think about what happens in the 19th century, maybe as a preliminary, there's a lot to this story on the side of measurement, what happens in geodesy throughout the 19th century. It's really interesting if you're interested in, the philosophy of measurement and the philosophy of experimentation, because so much is new there. Like the statistical methods, there's stuff going wrong, this is anomaly, and people are really not sure why. And lots of interesting work, both theoretically in the application of the, basically approximations using the potential function, which is new, come out of it. Like least square statistics partially comes out of it. Is really interesting. Okay, so I've written on it separately, and I think there's lots more to say than just Helmut's work. I just didn't want to put even more details. That's not the actual question. The actual question, I think of these as connected, and the key reason why I think they are connected in a way that's philosophically salient is that part of what's interesting is that you don't only get agreement in the geodetic measures at the macro scale, but in order to get that, right, essentially to deal with the systematic errors that plagued you before, you need to understand like rather short-range attractions. You need to understand, essentially you need like very well-developed solutions to the Laplacian potential function on the outside of, but Stokes works on that. He makes important advances. And I mean, you need then a geophysical understanding of the Earth's crust and mantle, which is also entirely new. And the good thing there is that essentially you're not only doing this micro-scale, meso-microscale work in the laboratory, but essentially you're scaling down from the measurements that you have at the time of Laplace, right? So I think this makes the appeal to evidential closure more forceful. The idea that you not just have convergence at two scales, but in fact like the gravitational effects you consider cover many different scales in that parameter space that you're interested in. So I think that's how they connect in the philosophical story that I tried to tell.
Let me try to repeat this back to you using slightly different words because I'm feeling very excited. In order to resolve the tension, what we really need to do is figure out the underlying physics behind systematic errors that we don't understand. And in order to do that, we need much more careful control over, in this case, physics at a different scale, the microphysical level, gravitation at the microphysical level.
That's exactly right.
Okay, awesome.
100%, yeah.
Chris, next?
Yeah, so thanks. It was a wonderful talk. So one of the things I was curious about is just how to think about even formulating the principle of additivity, right? And this relates to the question of how you think about forces. So there's one view which would say we might think of it as a active gravitational mass as a scalar quantity, and we're looking at that as additive. But you might also think of it as an additivity of forces.
Yes.
And this relates to the question of whether we think of gravity as like one fundamental force, and there's a quote by Herschel which suggested more like a Boscovician point of view, that there's just a force. At some ranges it looks like gravity, at some ranges it looks maybe different. So I'm curious how those sorts of questions interact, and is there a preferred formulation of additivity that these people agree on, or are they taking both sides?
Yeah, I hoped you were asking this because of your paper with Sri Biner on Newton's matter theory. I had this in my mind. I was thinking whether I should put something in. So I think the relationship between the additivity, so this I think generally is considered, maybe except Laplace, as a principle of the additivity of forces.
Okay, good.
Because otherwise it involves, for many, it involves a potentially problematic commitment to a specific matter theory, right? If you think, because, I mean, even Newton, he gets away with just saying, oh, it's proportional to the mass, right?
Yeah.
And I don't know the cause, I mean, it becomes weird once you ask, what is the weird cause that scales on the way up and down, whatever, if it's not, why don't we just assume it's the mass itself, right? Which is sort of also the conclusion you get from pointing in the end, like, I really don't want to say it's the mass, but you know, what else am I going to say? So yeah, the general view is, I think, additivity of forces, and then the interaction between that and matter theory, that then depends, I think, very much on your ontology, right? So for many, like Laplace, you know, it makes it really plausible to have a fundamental particle inverse square ontology. That's the basic constituents, right? And then they're just intertwined and you can't go any further, right? But as you said, there are clearly many people who also just thought, you know, you just have like some kind of point particles, you know, like in the Boscovichian sense. They're not exactly what Laplace had in mind, right?
Right.
Not unextended and so on. That's compatible, right?
Yeah. But by the end of the period you're talking about, it looks like they're also just thinking, after they've understood the forces of electricity and magnetism, how could it be? And that's why he's so, you know, gravitation stands alone, and that's disappointing, right? Because then it.
Yes.
Yeah.
Good. I should say more on that. There's a lot to say. I've spent the last weeks like looking through. There's a richness of material barely anyone has looked at of people in the 19th century. I mean, there's this work on the electromagnetic view of nature, right?
Yeah.
And then people speak as though this comes up with Abraham and Wien, and it has this tight connection to relativity, which is all true. But you have like people like Herschel and people like Faraday, especially in the 1830s, saying exactly the same thing, right? So I think, I mean, I'm not quite, I don't have the evidence yet to endorse this, but I think this was rather the mainstream view than the simple idea that some people think, oh, in gravity we just all remained Laplacians with some odd Boscovichians. I don't think that's right. I think most people were thinking, because the electromagnetic view of nature also has room for several relationships, weaker and stronger, between gravity and electromagnetism, right? You could think that you know, it reduces, so ultimately there's just electromagnetism. Faraday thought this for a while. Then at some point he thinks, oh no, you know, we somehow have to get gravity in whatever equations we eventually get for the electromagnetic interaction. So he does these funny things where he builds these cylinders in the Royal Institution, and he puts lots of wires around them, and he drops stuff in free fall. And you think, does it induce current? He really thinks you could get like a link between. So that's an even weaker form. There's this theory that Lorentz eventually adopts by Mossotti, where, like, I mean, the ether, the ether is sort of mechanically fundamental, and you have an attraction between ether particles and ordinary matter. That's a way to reduce it. So there's all these different ways, and I think the mainstream view that one of them will be true. Of course, you have to qualify Germany, France, England, US. But I was surprised how popular this is. It's just a sort of a sketch of the landscape of what's going on there, the link to matter theory.
Yeah, great.
Simon next.
This is all right. I feel I'm having a second go, but thank you. But I'm going to ask you again about something you didn't say.
Yeah, I hope I have an answer.
And this concerns really what was the weak equivalence principle, which was in Principia, and Newton's measurements on pendula with different materials and so forth. Yes. Was there a focus on that?
Yes.
I
mean, focus is wrong.
Measurement of different materials in Cavendish-type experiments.
Yes. I mean, most in Cavendish experiments, it's late. Pointing is very concerned with that. So so this is rather late, and it comes out of this effort to find some analogy to electromagnetism, I think, mostly. So this is second half of the 19th century. What there's before already is sort of analogous to Newton pendulum work, with different chemically composed, but also not a lot. And there you can see how Newtonian, I suppose, people were. The one person who stands out there is this German astronomer, Prussian astronomer, Friedrich Wilhelm Bessel. So he does a Newton-style test of weak equivalence, just more careful pendulum works, different substances. And it's quite interesting. I found this randomly when digging through the archive in his correspondence, in Herschel's correspondence. So when Herschel writes the obituary for Bessel, Okay, and he says, oh, he's such an empiricist, like such a good natural philosopher. He even questioned Newton on this, and he proved him right more than we thought. Then he gets letters, like 2 or 3 letters from German astronomers. Don't say this. Like Bessel, he was a Newtonian. Like you shouldn't put this in his obituary, sort of shaming his name. So there, I think it's more like individual curiosity, and then by the second half of the 19th century, it becomes a crucial concern for the microscale again. I hope this answers.
And can you just tell me when was it recognized as a fundamental principle, the weak equivalence principle?
As a fundamental principle.
At any time at all?
Like as in.
Was it ever given a name?
I don't know actually. I mean, someone here will know, I'm sure. I'm looking around for help, but like, as a name.
I'm worried about. I mean, it was clearly central to Newton's
Yes.
figuring out how to what I want to call how to represent this stuff going on. It was certainly fundamental to that way of handling gravity, but I don't know if it was. I don't think Newton ever.
Well, there's corollary 6.
Yeah.
Corollary 6. I
Yeah.
mean, this is absolutely essential. Then.
Yeah, but it's corollary 6 of the laws of
Yeah,
motion.
yeah.
He
Yeah,
refers
but
to it
I mean,
Proportionality to mass, right? He
Yeah.
uses that over and over again, right?
Yeah.
The rates
Right.
are always proportional
But I
to
guess-
mass.
Right.
I take it that's not the question, right? Like,
But that's sort of like giving it a name, right? That
well, I suppose.
Well,
this is what identifies terrestrial gravity with the interplanetary force. The argument that he gives for something like the strong equivalence principle, right? That Jupiter and its moons are all have the same attraction toward the sun.
Mhm.
I'm not sure if it's the strong equivalence.
Well,
principle.
no, the strong equivalence, I said something like, right? The strong equivalence
yeah,
is, I mean, I accept that Will taxonomy of the equivalence principle, but I mean, there's this laboratory, right, test particle test with
Yeah.
pendulums, and there's also this test with Jupiter and its moons.
That's it, yeah.
I mean, would it be right to say that this was all understood in terms of the equality of inertial with gravitational mass, as
Well,
opposed to
proportionality
universality?
of
I think that's right.
Yeah,
And-
is the term.
Right, and not,
That's right.
not
The
from
gravitational acceleration is always proportional to the mass of in the case of
Right,
corollary
right,
6,
right,
the
right.
attracted body.
Yes.
So I'm just wondering if it was sort of seen as something bound up with the properties of inertia and of mass, as opposed to properties of space-time and forces, if you know.
I think. Well,
I have an historical conjecture.
okay.
Okay, Newton does say that, in effect, gravitational mass is proportional to inertial mass, and he's got these, experiments with the
Yes.
pendulum and stuff like that.
Yes.
But as Miguel pointed out, in the 19th century, there was this program of electromagnetic theory of matter, which, if successful, would have embraced everything. People thought that we were hoping to have gravitation be an electromagnetic phenomenon, and if that's true, it's absolutely natural for gravitational mass to maybe vary with charge, right? And and Newton's experiments were all on electrical Newton things. So my conjecture is, when does this become a foundational important principle? My conjecture is with Einstein.
Yes,
Yes.
yes.
And we retroactively think that it was regarded as foundational in importance since the time of Newton because we forget so much of the history.
I think that's
That's what I like about your talk. One of the main things I like about your talk is your emphasis on the gravitational program as an open-ended research program with open to alternatives, right? And electromagnetic theory in the 19th century was never a settled, completed theory. It was a long process of theory construction, and I think that's important because philosophers often want to compare completed theories.
Mm-hmm.
And the more I look at history, the more I become aware that how rare completed theories are.
That's right.
And the picture a lot of philosophers have is someone formulates a theory, and then for a while everyone is more or less complacent that this is right, and then it gets overthrown. And that just doesn't really seem to happen
Yes.
very much. Very much.
It's very nicely in line with something that I take it, at least me, like Howard Stein taught us, right?
Yeah.
About the importance of knowing the empirical, the empirical scenarios for testing to understand the structure of a theory, right?
Yeah.
Like that teaches people to identify serious theoretical alternatives that they might not even be aware of. In the version of the theory developed, and then as a corollary, it becomes really important for the evolution of the theory over time.
Yeah. Very good.
So I couldn't agree more.
You're next on the queue, Alan.
Okay, thanks. It struck me that one of the reason we often think of the measurement of the Earth, the geodesy, is especially in the late 18th or in the 18th in the 18th century is the controversy over Cartesian vortices.
Yes.
And I mean, I realize my vague sense is that Newton, of course, tried to respond in various ways to whether you could even come up with a consistent Cartesian vortice mechanics and so on. But was that in mind when people were thinking about geodetic measurements? That's just what I was thinking. Okay, thanks.
Yeah, thank you so much. Yeah, I'm glad you asked us. I'd love to talk about the 18th century. So, yes, I mean, so different stages to my answer. The first one is there's a lot of confusion in textbook history, even in the literature, on the importance of that specific test, this expedition to Lapland and to Peru, what it established, and so on. So one thing to say, it's the first part of the answer, is that the link between sort of a broader vortex mechanics, sort of for gravity, and this particular test was very weak indeed. So the people who believed in the oblong Earth, right? There was mostly this was just observational astronomers, the Cassinis, and they were actually quite non-committal as opposed to the vortex theory. It's just there were some people who took it to conform to vortex theory. There were many crypto-Newtonians who still sort of believed in these measurements. There's this one important person who writes on this is Desmarins, who's the secretary of the Paris Academy. He comes up with a completely new phenomenological definition of gravity, such that given that we take from observation the Earth to be oblong rather than oblate, how does it have to define gravity as a function of latitude such that it accounts with the observations without giving a cause, just sort of as a function of the radius? Completely non-committal in France. So it's much it's a bit complicated. Certainly, what is true that it's historically important that the confirmation that the Earth is oblate for Newtonianism. I mean, whatever that means. I mean, for Newton to become more influential in France, but there's a lot of social dynamics going on with Voltaire and Maupertuis and so on. What is my favorite point about this episode in the history is that it's just not true at all that these measurements in Lapland and Peru, in a very strong sense, confirmed the Newtonian gravitation. Why is that not true? Because it is true that there's an alternative theory, which is Huygens' theory, which is, I guess, a vortex theory of sorts, but essentially just committed to simple variation of gravity with distance, not universal. And it gives you a polar flattening of the Earth that's equivalent to what you get on the Newtonian theory for the very dense core, right? So much less flattening. Now, what the measurements show is that the results are much closer to the Newtonian homogeneous case than to that case. The problem is no one had developed the theory of stratified equilibrium by the time. It turns out, once you have the interval that's permissible with Newtonian gravitation for rotation under equilibrium for the centrifugal force of the Earth, the measurement that Maupertuis does, together with the other measurements at the time, falls outside of that interval. So it does not. In some sense, it's closer to that than the Huygens theory, but the flattening is too large, even for the Newtonian theory. And the biggest anomaly in that graph by Laplace that I showed you is that measurement. It's the biggest problem, and it's in fact discarded eventually and redone in the early 19th century. So it's so confusing that the standard story is Newtonian universal gravitation was tested by Maupertuis. Well, in some sense, it convinced the French that it's a better program than just simple inverse square force. But it's very weak evidence, and all the sophisticated people like Clairaut and Laplace realized this very clearly it's very weak evidence, was very weak evidence for universal gravitation. The best proof of that is that Clairaut, 7 years after he wrote this book, when he comes up with the extra term in Newton's law, given the anomaly in the lunar orbit, he says, oh, there's further evidence for this. It's the fact that Newton's theory doesn't get the shape of the Earth right. Of course, the short-range forces would also affect that. So well, it's very confusing to say it's a test of universal gravitation. I mean, I could go on, but yeah. Yeah.
Actually, now that you mention it, I had a question about that interval.
Yeah.
Is that derived under the assumption that if there's variation in density, it increases as you go down?
Yes, that's the
Okay,
assumption.
so the extreme points would be uniform and mass concentrated at
That's right.
at the center.
They're
Okay.
concentric. And it also relies on an extra assumption in Clairaut's derivation that the ellipticity is the same for every layer. The number is arbitrary,
Right.
which
Okay.
makes it so hard that both the... Sorry?
So it's just shells.
It's exactly like
Yeah.
the number of shells is arbitrary and the individual width is arbitrary. It makes it so hard to learn anything about Earth's internal structure from surface gravity measurements, and you need seismology to do that. But for Clairaut, there's the further assumption that they have to be ellipsoids, all the shells. Now, what Laplace shows is that you can slightly relax that. They all have to be ellipsoid, but they don't have to have the same ellipticity, as long as the ellipticity is increasing outwardly, so that the largest ellipticity is the surface and the smallest ellipticity is inside. So that's the sort of final theory, but it makes very little difference because we have so little access to the internal structure of the Earth, so that basically the final theory is Clairaut's, and Laplace makes the proof a bit nicer, but it doesn't bear a lot on empirical observation.
Very good, thanks. Robert, it's the last question. Can we pass this down? To where? There we go.
I'd just like to, well, first I'll say thanks. That was a really great talk, and I think a great tribute to George in spite of slight disagreement.
Thank you.
But just to return to a previous point quickly, I do think that if no one else did after him, Newton certainly made the proportionality of weight and mass fundamental.
Okay.
It's so crucial to his argument against mechanical explanations, and it's really central to the identification of the interplanetary force as gravity, that it shares that feature of proportionality in weight and mass. And if I have another moment, I just wanted to say I thought there was a really interesting connection between this and Lydia's talk and the discussion of the PPN formalism, because that really was motivated by a kind of pursuit of alternative theories, like Machian, especially Machian alternatives in the first place to general relativity. And so that the quote you had about showing what features gravity does not have seems to be something really important that emerged also from the PPN testing that seemed to fix all the parameters so closely around GR.
Yeah, thank you. I really appreciate it. I think that analogy is correct, which is why I had to think of Simon's comment during the talk to say how unpopperian this quote by pointing is, right? Very unpopperian. But I agree with you. I took Simon's question to be. Well, no, I think you're right. Yeah. I think you're correct. It's right to say that Newton identified it. I just think the framework under which it was, like the context in which the equivalence that Newton identified was considered, is quite different to what we then come to know as the weak equivalence principle. Well, anyway, we can talk about it more. I appreciate the note.
Can I just say, you're absolutely wrong. You're absolutely right about Newton, but I think that his successors did not understand well enough.
Well,
yeah, that's
one
what I'm
exception
thinking.
is Du Châtelet, right? And George always emphasized this incidentally, the way she made a big deal out of gravity proportioning itself to mass.
Yeah, Laplace was very aware of this. Laplace makes a big deal out of it too. When it comes to, this shows up in the, something that George and Howard Stein wrote on, which is the applicability of the third law to gravity, right? And then in the way that the result by D'Alembert and Euler is interpreted when they managed to derive the precession and nutation of the Earth. So the nice thing about that is you can show you have like the change in the rotational axis, and you have two changes, right? Well, first a big wobble and then a small perturbation on the big wobble due to the moon and the sun. And you can compare their size. And you can you have independent determinations of the mass of the sun and the moon from astronomy, and you can compare if the proportionality generalizes. And in these discussions of that result, you can, in Laplace at least, like you can see an appreciation for the importance of something like the weak equivalence principle. It's certainly not discussed a lot. So in some sense, I think everyone is right.
They discuss corollary 6.
No, Laplace doesn't refer to the Principia. No. But I'm sure some of the British, like in the British tradition, they would have done.
Well, that's an important part of the importance of what we say, but just emphasizing that as essential to the unification of terrestrial gravity and interplanetary diffractions.
Yeah.
Okay, I think we have to wrap it up because we won't have time for one speaker. Let's thank our speaker.
Thank you.